initial population of rabbits on a farm was 50. The population increased by 7% each week. How many rabbits were present after 15 weeks, 30 weeks? How long would it take for the population to reach 500? So, this is an applied geometric sequence question. Now, you might not realize initially that this is about geometric sequences. I will show you why. So you start with 50 rabbits, and we'll go into what term this represents in a minute. But basically, I need to, each week I increase by 7%. Now, the way to do a 7% increase, if you can remember back to your percentages, back to interest applications like that, if you multiply a number by 1.07, that increases it by 7% in one step. So this is a multiplicative problem. So every time I multiply by 1.07. So that means this is a geometric sequence question because you have a starting term. Well, all sequences have a starting term, and they have a constant common ratio, not a common difference. This is being multiplied each time, not added. It's not adding the same amount of rabbits each week. It's the population is increasing proportionally to the size of the population itself. So why have I put a little circle here? It's because it tells me the initial population was 50. So actually this is a 0, because if you think of what the rest of the question looks like, how many rabbits after 15 weeks, 30 weeks and so on, I want to be able to put in n equals 30, so n equals 15, n equals 30 into a formula. If I use this as A1, then that's not going to work. It's going to mess everything up by a week. So really the initial is A0, it's the term before the first term. So A1 would be, well, whatever 50 times 1.07 is. So basically, what is 7% of 50? Well, 50 equals, say, 100%. So that must mean that 10% equals 5, and that must be 0.5 must equal 1%. So 7% must be 7 times that. Well, 7 5s are 35, so 3.5 rabbits. 3.5 rabbits must be 7%. So your A1 is going to be, according to this rule, is going to be 50 plus 3.5, so it's going to be 53.5 rabbits as A1. So now you have a GP, or a geometric sequence, with A1 equals 53.5 and R equals 1.07. So for this sequence, you know that AN, as in the number of rabbits in the population after n weeks, equals A1, 53.5, times R, 1.07, that's the multiplier, to the power n minus 1, with n being the weak number. So now it should make the rest quite easy. So how many rabbits were present after 15 weeks? So you want A15, well, that's going to be 53.5 times 1.07 to the power 15 minus 1, so to the power 14. And that is 137.95. 9515, blah blah blah. So I reckon around that to the nearest whole rabbit, so at 138 rabbits. A2 was how many rabbits were present after 30 weeks. So I just need A30, number of rabbits after 30 weeks. Well, that's going to be 53.5 times 1.07 to the power 30 minus 1. 30 minus 1 is 29. So that gives me 380.6127 blah blah blah. So I'm going to round that to 381 rabbits. Right, so part C, how long would it take for the population to reach 500? So you need to know when is 53.5 times 1.07 to the n minus 1, when is that greater than 500? Well, I suppose greater than or equal to, because it says how long for the population to reach 500. Now, there's multiple ways to do this. Technically, we assuming that you don't know logarithms yet, although they are in the IGCSE and they should have been covered. So logarithms would be a good method. If you're going to have to use a calculator anyway, so the calculator has various functions that can do it. You could just type it into an equation solver. You could use table mode to do it, or you could plot this as a graph and then plot the graph of y equals 500. Plot the graph of y equals 53.5 times 1.07 to the power x minus 1. See where they cross. So I reckon actually I'm going to do it like that. So I've decided I'm going to use a graphical method to see when how many weeks it's going to take for this rabbit population to reach or pass 500 rabbits. So we're going to go to menu and graph, and we're going to type in y equals 53.5 times 1.07 to the power of x minus 1, because we don't have an n. So y equals 53.5 times 1.07 to the power of x minus 1. And I'm going to draw a second line, which is y equals 500. So that's the line of 500 rabbits. Okay, execute and draw. And then we're going to have to adjust the window quite markedly. So if we go to V window, thinking about what you're going to need. So firstly, you know your Y max. Well, we've got 500 rabbits on here, so we're probably going to go a bit beyond 500. So I don't know, maybe 550, something like that. Y min, not so, yeah, that's all right. I think X min, again, isn't important. X max, well, it's probably going to take more than 6 weeks. So I don't know, if we guess maybe 50 weeks, something like that. Hopefully when we go back to it, we can see a graph. Ah, there we go. So that looks nice. So this is the rabbit population growing after so many weeks. And this is the line of 500. So we're interested in when does this rabbit population reach 500. So we're looking for the intersection of those two lines. So if we do Shift and Gsolve, we're looking for intersect. And you can see, it's not showing up brilliantly, but that number says 34.0328381 and so on. So after 34.032 weeks, this population reaches 500. So that tells me that n needs to be greater than or equal to 34.032. So it's going to take 35 weeks, or in week 35, for population to reach 500.